So today we're going to be quickly going over how to perform the same naive matrix multiplication we did in the last video, but this time using GPUs. So today we're going to be using CUDA on NVIDIA GPUs, and in the future I can show you how to do the same thing on any GPU using something like Vulkan API, DirectX, or OpenCL or OpenGL or what have you. So today we're going to be focusing specifically on CUDA. So for CUDA, which is, to be honest, the simplest one. So for CUDA, what we're going to do is we're going to make a file that ends with the extension .cu. So I'm just going to call this CUDA, which is a bad name, but yeah. So I'm going to call this CUDA, and what I did was just paste the text that we had, the code that we have from the last video. So this is exactly what we had in the last video, and we're going to keep the timer, and what we're going to do is again, we're going to keep mat mul, we're going to keep print, but we're not going to keep the stress algorithm because that, like we talked about in the last video, is not going to apply for it's going to be recursive, so it's not going to be useful for GPUs, or at least in the way that I'm showing it. So we're just going to delete that. And so first we're going to do a sanity check of like, is everything still working correctly? And now we don't have to make it a square matrix, but it's already a square matrix, so I'm just going to keep it that way. But this should work with any shape matrix. Okay, so to run a CUDA code, essentially what we're going to do is use NVCC. So I'm running this on a Linux system, and you say NVCC and then the file name, and typically I just like doing ./a out, just run it in one code. So essentially what we're doing is this is the compiler that we're using, and then the CUDA file, and essentially we're just going to do a out. So it's a CUDA file, it's essentially a C++ file, to be honest. And that should print us perfect. That should print up the result and the time it took. So this is very, very small. The time is very, very small, just because the matrix size that we're using is very small. All right, so what the heck do we do for running on the GPU, right? That's the question. So what we're gonna do here is we're gonna define a set of variables, and these variables, they're gonna be used by the GPU. So I'm gonna call them, instead of A, B, and C, I'm gonna call them A GPU and B GPU and C GPU. And for each of these, what I'm gonna do is I'm gonna set them to null pointer, and they are all going to be float pointers. Okay, so they're all going to be float pointers, and then we're setting them to null pointer. Now what we're going to do next is we're going to allocate some memory on the GPU for these guys. So how do we do that? What we do typically in C or C++ is we use malloc, right? But because we're doing this on the GPU, NVIDIA has been very kind to make things a bit consistent and calls it CUDA malloc. So it's CUDA malloc, and then you pass in the address of the address of the pointer. So you're passing in a double pointer, the address of the pointer, and then you're going to pass in the size of float times what we're doing here is we're doing m by n for a, right? So size of float times n by n. All right, so we do that, and we repeat the same thing for the others. So CUDA malloc, B and C, and the sizes accordingly, we're going to keep them accordingly. So n and k and m and k. All right, awesome. So we allocate the memory. Whenever you allocate memory, what do? You free memory. How do you free memory in C or C++? You use the free. Here, again, NVIDIA has been very nice, and we don't have to do other fancy things. We just have to call free, or CUDA free. All right, so what we're going to do here is, now that we've allocated memory on the GPU, we're going to copy the stuff from the CPU side to the GPU side. So how do we do that? Again, how do you copy in C or C++? You use memcopy. Here, we're going to use CUDA memcopy. It's that simple. CUDA memcopy, and then we're going to pass in the address and the source address, the destination address and the source address, and obviously the size that we wanna use. So I am quickly gonna go over change these up. B and C. All right, awesome. So the next thing that we need to do after we copied our memory is tell it who am I copying what to. So essentially, there's going to be, we're not done with this yet. Essentially what we're going to do is we're going to say CUDA, we're going to say memcopy is being performed from host, which is the computer that I have, my PC, on the CPU, not my PC, the server on the CPU, to device. Device being the GPU. So we're saying CUDA memcopy is happening from host to the device, right? Sorry. Now, actually, this is a bit tricky because C is a special case because C is the output. We're not going to use this. What we're going to do is we're going to copy from the device. We're going to say, hey, C, populate this guy, the destination, using the C GPU. So here we're going to perform the operation, the mapmul. We're going to perform mapmul, and then the result of which is going to be C GPU being populated, and then we're going to copy from C GPU to C. And then how large of the file, we already know that. But this time, what's going to change is we're going to say CUDA memcopy, and then we're going to say device, the device to host. So we're going to say we're copying from the GPU to the CPU. All right, so now what we're gonna do is actually perform the operation, right? So I'm gonna preface, we're gonna have to define a kernel, and a kernel is just the function that runs on the GPU. So, or the kernel function is the one that is the function that runs on the GPU. So first we have to give the dimensions of the GPU. So the GPU, we're gonna have like a lot of blocks, and then within each block we're gonna have like different threads. So my CPU like has my personal computer has like 11 CPU cores, so I can run like 11 parallel threads. But GPU, you have like so many threads. That's the power of the GPU, right? So essentially what we're going to define is the grid. So there's different ways to define this, and I highly encourage you to go to the NVIDIA docs and see this. But today I'm going to keep it very, very simple, and then I'm going to say dim3 is just it's pre-provided by the CUDA in CUDA. So what I'm giving it is I'm going to say, hey, the dim block, and again, this is another function that's like predefined. So I'm going to define a 16 by 16 by 1 block. So this means that we're going to have, this is going to make sense when we write the kernel, but this means we're going to have 216 times 16, which is 256 chunks, like different indices that we're going to get. Essentially, that's what it's saying. And I'm going to show you what that actually means in a second. So the other thing that we need to define, I'm going to gloss over this very quickly because we're going to come back to it, is the grid dimensions. So dim grid, and then this is going to be typically, now what people typically do is 16, what we have here, and then we're going to add to this, the actual like size that we're looking at. So let's say we're defining this to be X and this to be Y, right? So we're going to say M plus 16, and then we're going to say over M, or over 16, sorry. So that's what we define, and people typically add a -1 here. So this, you might recognize this as ceiling division, and that's essentially what we're going to be doing. So to make things simpler, I can just cut and paste this inside, but I'm going to write a little lambda function here, and also to flex to some degree. And I'm just going to call it auto ceil divide, and you can see I come from Python by using snake case, but I'm presuming that you guys already know how to do lambda functions in C++. So that's essentially what we're going to be doing. So return this guy, and obviously I'm going to change this to X and this to Y and this to Y. Awesome. So now that we have our little lambda function, I'm going to define the grid as being ceiling divide, and then 1. Okay, we're going to ceiling divide M by what this block dimension is, right? So we're going to say dim block dot X, and then we're going to call n comma dim block dot Y. So we're essentially saying that we're going to have like a 2-dimensional grid, and the first dimension is the M, and the second dimension is the Y dimension is N. and the z dimension is we're gonna see it's just gonna be k, and we're gonna define that within the kernel. And again, we're gonna do that in a second. So just to keep things tidy, I'm gonna put this there. Okay, so the last thing that we're gonna do, I'm not actually gonna show you right now, you're gonna see why it's important as I write the kernel. So let's actually write out the kernel. So I'm just gonna call the kernel some function called kmol or something, kernel for mol. And typically this is how you define, or this is how you call the CUDA kernels. So this is like overloaded or something, but like you give the grid dimensions in here. So you say this is the block size, this is the grid size in here, and these like three less than or equal to signs, like bit shift signs, or less than and equal, less than and greater than signs. And within this, you're going to pass in the parameters. So in our case, it's just going to be a GPU, B GPU, C GPU, right? And then we're going to come back and then actually like define what this function is. So when we define what this function is, what we're going to do is, I'm going to define it here. So what you're going to do is you're going to say something called, put something called global right in front of the actual function definition. So, and I will refer you to the, again, NVIDIA docs to learn a bit more about this. But there's going to be a void function, and I called it kmol if I remember. Yes, I did. And we're passing in a float pointer called a GPU, and then a float pointer called B GPU, and then another float pointer called C GPU. All right, awesome. So let's actually define this function. So what I'm going to do is I am going to use, there is no way that these are going to be, and you don't need to do this, but I just like using unsigned ints, but there is no way that these are going to be negative values. So I typically like using unsigned ints. So uint, the row index, which I'm going to call Ri, is equal to, now this is what we defined earlier. So we said the row corresponds to the x dimension of the 2x2 grid, right? So we're going to say block idx, which is the block ID, dot x, and sorry about that, I have to restart. So this is the block ID. So what block are we on right now? After we define that, like let's say we are on block 2. So each block has different threads, right? How many threads does it have? It's going to have block dim, that's the block dimension, dot x. So it has these many threads. And then what thread are we on right now? Thread ID dot x. Okay, I think that's how you do it, or how you spell that, but yeah, so that is the thread that we are on right now. So we multiply by the dimension and then we add the thread. This is very basic, like stuff that we did like right up here, right? Similar stuff that we did right here. Okay, so after we did this, we're gonna do the same thing for column, and we're just gonna call those y's. Awesome. So after we do that, it is very good practice to always check if we are still in bounds before we perform our operation. So we do that by is Ri less than the actual m, the row that we have. Now we don't know what the row that we have is. So to do that, we're gonna have to pass in another parameter. Now, instead of passing in a whole other parameter, what I'm gonna do is pass in one parameter, and we're gonna perform the same thing for like the rows as well and whatnot. So I'm gonna pass in one parameter that is a struct. So I'm gonna call this PC for push constant. And you might be familiar with that if you use Valken. I use Valken first, so I'm used to that. That's why I'm using push constant. But we're just gonna call it PC, and we're gonna define PC here, and it's just gonna be the m, n, and k that we had earlier. And we can just call these integers m and k. Yeah, so push constant. So we're gonna say push constant dot m, is it less than that? And is ci less than push constant dot n? All right, or sorry. Yeah, this would be n. So we check those two, and then after we check those two, we proceed to our actual function, right? So we're gonna say, again, I'm gonna call this a uint, and we're gonna say, let's just call this a GPU M1 and matrix 2 and then matrix, okay? So what we're gonna do is matrix 1 index, the index of matrix 1, which is a GPU, well, I guess I can just call it a GPU, I just don't want it to be too long. but a GPU's index is gonna be what? This is the same thing that we did earlier. It's the row multiplied by the size pc.n by the number of columns, and then to this we're gonna add the index, right, of k, but we haven't defined that yet, and there's a very good reason why we didn't do that, and I'll show you in a second. But first I'm gonna do the same thing for b, and that's gonna be k. All right, so the reason, or sorry, we don't need to do this here, and I'll show you why. So the reason why we're doing this is because we have to, in here, we had to do a plus equals, right? So the plus equals, you cannot do on a GPU. You're gonna have data races, like I briefly mentioned before. So what we're doing here is we're using the kernel for these two for loops, and then within the kernel, we're gonna perform this operation. So that's essentially what we're doing here. In fact, it's so close that I'm gonna do this. I'm gonna cut and paste it. So I wasn't planning on doing that, but yeah. So it's so close that we can do this. So we can say ki is at 0, and then ki is less than, I guess we can say push constant dot, maybe I lied, yeah, this should work, okay, push dot constant dot k, and then what we're gonna do is we're gonna index this out, but we can't do plus equals again. So what we're gonna do is float sum, and then we're gonna call this 0.0, and then add that, and then finally define cGPU, and then the index of cGPU is gonna be sum. That's what we're gonna do. And we also need to define what the index of cGPU is, and that would be another uint, and that's just gonna be the row index multiplied by the push constant dot k plus the column index that we're on right now. And yeah, well, okay, okay, the way I'm writing it out right now, it's gonna pan out the same way, but the way that I wrote it out up here right now, we're actually using the column index s or CISK. So I'm just gonna, that's what I was confused about a bit earlier. Okay, I am just gonna replace these, and the column index is going to be k, so bGPU is probably going to index. We don't need to multiply by anything, and the push constant dot n. Okay, so instead of c, I guess that's what I get for suddenly changing my code, but instead of c, we're going to do sum plus equals, and then what are we going to multiply, right? So we're going to multiply a GPU, and whatever we indexed of a GPU plus ki, right? This guy. And then same thing, whatever we index of bGPU plus plus ki. But not just plus ki, it's gonna have to be plus ki times push constant dot k. Now, the reason is we have to, this gives us the index of k, like the k index that we're on right now. And then again, these are like not properly labeled. I should probably just call this j or something. But this would be the actual, like the size, the index j that we're on right now, and the size of index j, and where on index j that we're on right now. So similar story to what we were doing previously, like in fact to here. So this, you can parallel it by doing this, plus bGPU I. All right, so see, it's the same, you can kind of tell the same story by doing that. Okay, so we're properly indexing out the sum, and then finally we replace this by the actual sum, or populate cGPU by the actual sum. So after we perform this operation, like this runs on every cell of the output, and then that should give us a populated cGPU, which we then later copy, and then after we copy the cGPU, it should be able to, it should be okay to free the GPUs, the allocated memory. And what we can do afterwards is we can print, I think that's, yeah, okay, we can print C. Now, we can compare these two. I'll turn off the timer for now. But here I want to mem set C to 0, and we'll do this. All right, so just to be sure that C is set to 0, I'm gonna not run this code and see that we're okay. And we are not, apparently. Okay, sorry, it looks like I had a few typos there. So this is supposed to be AGPU, BGPU, and CGPU, another cut and paste error. And here we need to define actually what the push constant is. So we need to say push constant PC and then M and K, and actually define that. And you see that this MNK is going to give us a warning. And the reason is, and I purposely did this, is because in the previous code we had a size T, and this is not going to do an implicit conversion from size T to int. And the reason I'm using int here is to in the push constant. You don't need to use int in CUDA kernels, but we're going to have to use int like 4-byte integers, whether signed or unsigned, for actual like Vulkan implementation and size T. So I'm just going to narrow this down to int here. So after you do that, and you remember to put a comma in your push constant, you're going to see that yes, this does work. They're exactly the same. It gets cleared, and then what you see is that the CUDA and the CPU matrix multiplications are the same. So now the last thing that I want to show you is actually time this. So I'm going to show you two things, and for each of them, I'm just going to turn off printing, and what I'm going to do is actually do 1064 for each dimension. And I can use a const expression, which I probably should be using, to be honest with you, but I'm kind of lazy, and I'm going to cut and paste it. So essentially what we're going to do here is we're going to time it in two different ways. So I will have a timer here, and then I'm going to do the same thing, very lazy, if0, else, and if. All right, so that should just run the CPU, and in the else case would run the GPU. So I'm just going to start with the CPU, and remember to add that. And what you're going to see is this, it's going to take a bit long, like 3 seconds, right? So the next thing I'm going to do is run down the GPU. Now what you notice is we're doing all of this allocation stuff, right? And that takes time. So let me show you how much time. Now I'm going to run it on the GPU, and then you see it takes like 3 seconds, right? So what I'm actually going to do is I'm going to place this timer, and I'm going to place it right before we actually start performing the matrix multiplication operations. And to be honest, we're being fair by doing that, because that's what we're doing on the CPU side. So when you do that, you see the reduction that you get. So when you have a lot of allocations and reallocations in memory, like if you're running a neural network or something, it's better to allocate once and then reuse it multiple times. And we can talk about that in the future as well. So the last thing that I would want to show you guys is I'm going to show you an actual code that I work with and that I use on day-to-day. So I'm going to cut and paste the kernel for you. And essentially, to give you context, this kernel is for performing matrix multiplications on, it's for performing them for neural networks. And the idea is what happens if we have a case where we have to batch our matrix multiplication. So it's not just like 2 by 2, but it's a tensor of like arbitrary dimensions. So what happens in that case is we're going to have to define another dimension. So it's going to be like, in a very naive sense, it's going to be like a cube that we define, not just like a 2D grid. And the z-axis is just going to show us the batch dimension, and we're going to add like a given stride for each batch. Like for we're going to add the batch dimension, like the bi, multiplied by whatever the batch size is, and that would be like the m stride, or m1 stride, m2 stride. M1 stride, m2 stride, they're just the size of one 2 by 2 matrix, right? So, or if you have a 3D tensor or however many dimensions you have, just convert it accordingly, right? So you can see this would perform any arbitrary shape tensor. It's going to perform a matrix multiplication on it. So I hope that was helpful. I will put this up on GitHub, and I probably sometime soon discuss how to use Vulkan APIs to perform these matrix multiplications, or even show you some neural network examples that I work with for convolutions or any other operation to make them much faster and like benchmark the actual speed gained. All right, thank you.